It's not working. Stop me. So,
It sounds good.
okay, great. So I'm Dan Titze, and I'm going to be talking today about real-time forecasting in the Great Lakes, and specifically looking at some research that we're doing on improving simulation of coastal processes and coupling the water and land domains. So, as Jay mentioned, I went to grad school in the Water Resources Science program at University of Minnesota Duluth and worked in Jay's lab. Did a wide variety of things there. I had a big focus on Lake Superior thermal structure observations. So we did a lot of work on the blue heron, deploying and recovering moorings, and looking at what those data sets tell us from a climate perspective, and specifically in terms of winter conditions and under ice conditions on Lake Superior. Um, in my PhD, I moved on to more focus on ice. So I did a lot of work on ice and climate dynamics in the Great Lakes, specifically Lake Superior, and worked in Jay's lab for a couple of years following my PhD, where I maintained some weather buoys and did some estuary modeling, which leads in nicely to some of the work that I'm doing here at GLERL that I'll be talking about today. Um, Bounced around a little bit from there, but I joined the Cooperative Institute for Great Lakes Research in April of 2019 as a hydrodynamic and wave modeler. Um, SIGLR, as it's called, is our cooperative institute. So we work very closely with them here at GLERL. And then earlier this year in February, I joined GLERL, the Great Lakes Environmental Research Lab, as a PI in hydrodynamic modeling as a physical scientist here. And so that's where I am now. It was a pretty smooth transition. We all sit in the same office and work very closely together. SIGLR is a department at University of Michigan, but there's a consortium which University of Minnesota Duluth is part of, which makes it easier to collaborate on projects. And so we've got a lot of collaborations with partners who are part of the SIGLR consortium throughout the Great Lakes. And there I've been doing modeling work. So working on the Great Lakes forecast systems, I developed a flood forecasting system for Lake Champlain and have been doing some research on coastal coupling in our models. And these are the three things that I'll talk about today. And so I'll start with a little bit of background. I'll give a quick introduction on what the Great Lakes Environmental Research Lab is, as well as our operational forecast system, which produces simulations and forecasts of conditions throughout the Great Lakes. And then I'll get into some of the ongoing research we have going on in coastal coupling, and specifically look at the development of a flood forecast system for Lake Champlain. And as part of that, I'll kind of walk through what goes into a hydrodynamic modeler. Um, I imagine this group is a pretty diverse group in terms of your areas of study. So I like to kind of not assume that everybody knows exactly what hydrodynamic modeling is. And I'll kind of walk through some of the steps of how we set up a model like that. And lastly, I'll get a little closer to home and talk about some modeling that we've been doing recently in Duluth Superior Harbor and looking at our ability to simulate some recent flooding events there. Um, So the NOAA Great Lakes Environmental Research Lab, where I work, is a research lab in Ann Arbor, Michigan, and we have a field station on the western side of Michigan on Lake Michigan. And our mission is to conduct scientific research on the Great Lakes and coastal ecosystems, develop and transition products and services, and share knowledge and information to advance science, service, and stewardship. So NOAA is sort of divided into groups that do research and groups that do operations, who operate and maintain products. So we're on the research side of that. And we have three research branches. We have the Ecosystem Dynamics branch, or EcoDyn, who does, as the name implies, work on ecosystems research throughout the Great Lakes. So harmful algal blooms, invasive species, some fisheries work, that sort of thing. We have our Integrated Physical and Ecological Modeling and Forecasting branch, which is a mouthful. It's IPEMF is the acronym, which in itself is a mouthful. And that's the branch that I sit in. That's our modeling and forecasting branch. And so I'll be able to go into a little bit more detail on that. And then our third research branch is the Observing Systems and Advanced Technology. They do a lot of the shipboard work. They deploy and maintain our network of buoys. When we're doing moorings and that sort of thing, they deploy those. They have underwater gliders. And they also have a research component. So they're doing research to advance and apply new observing technologies on the Great Lakes. And so again, I sit in the modeling branch, the middle one here, and one of our flagship products is the Great Lakes Operational Forecasting System, or GLOFS. GLOS is a set of 3D hydrodynamic models that simulates physical processes throughout the Great Lakes. And ultimately, it provides near real-time guidance on physical conditions. So things like water currents, water temperatures, water level fluctuations, so storm surges, and recently ice cover. And it produces 5-day forecasts of these, as well as a representation of the current conditions. It's built on a model called the finite volume community ocean model, which I can talk about in a little bit more detail later. And this is an example of the grid resolution. So this is a zoom in on the Straits of Mackinac here. And the resolution of these models gets down to about 200 meters along some of the coastlines and areas of interest, like you're seeing in the Straits here. And then as you get farther offshore, the resolution's a little bit coarser where things aren't quite so dynamic. And so twice per day, we're producing updated simulations and forecasts on current conditions. So you can go to, our website or the operational website and get real-time images and forecast animations of what we're predicting for conditions on the Great Lakes. And so this sort of fills in the gaps between some of the observing locations. So there's a handful of buoys throughout the Great Lakes, and those are providing real-time data. But what's going on in between them, what's going on in the winter when some of those buoys aren't deployed, and what's predicted through the next several days is sort of the realm of these modeling systems. And these fit into the National Forecast System. So the same way that there are atmospheric weather models like you would see on your evening news forecast, there's these operational lake models, and we ingest information from those other operational systems. So we use those sorts of weather forecast models to inform the conditions that the lakes are experiencing. So that's one of the main inputs. Things like wind, air pressure, air temperatures are all things that are going to affect the conditions on the lake and that we feed into our models. There's also hydrologic data or models. So we use information from river gauges or the National Water Model, which is a national model that simulates river flows and stream networks throughout the country. And that forms the basis for our operational forecast system. And again, this provides information on physical conditions. So those water currents, water levels, et cetera. And that can be used as the basis for other downstream models. Somebody interested in ecology might create a biophysical model using the output from our models to forecast things like harmful algal blooms or hypoxia. Sediment transport or oil spill modeling is another area that we're getting more into here at GLERL. We have a new center of expertise in collaboration with the Coast Guard to do more oil spill modeling. So that's going to be an area that we're getting into. And to inform those oil spill models, we would use our operational Great Lakes models as the baseline conditions. So we do the research and development on these models here at GLERL. We're, again, a research lab. And once we have a well-tested, well-validated project, we would transition it off to an operational center, which would be a completely different organization, although we would work closely with them through those transitions. And so we do the work to develop these grids and test them. And once they become operational, that means that they're maintained 24/7, 365. They're maintained around the clock. So if they go down at 2 in the morning on a Saturday, somebody's getting out of bed to fix it. And so Lake Erie was the first of these models to transition into operations, Lake Michigan Huron in 2019. And just last month, we finished transitioning the last of the models into operations just last October. And in addition to that, we added ice cover forecasts to all of the Great Lakes. And so now all 5 of the Great Lakes are in operations and they're part of the National Forecast System. And that sort of research and development starts here at GLERL. And so that's one of our main forecast products, and that forms the basis for a lot of other modeling that we do at the lab. In addition to those hydrodynamic models, there's a series of wave models for the Great Lakes. These are built on the WaveWatch 3 community wave model, which again is another model that I'll talk about a little bit more in some of the other work that we're doing. Similar to the hydrodynamic models that forecast water levels and currents, these forecast surface waves out about 6 days into the future. These are operated by the National Weather Service, National Centers for Environmental Prediction, But we, again, work closely with them to develop these models and have a lot of ongoing research to improve them. And particularly right now, we're focusing on improving wave forecasting in the winter when ice is present. So waves are going to have or ice is going to have a damping effect on waves, and we're trying to capture that and parameterize that in the model. And that'll be an upgrade that we hope to add to a future wave forecast system. And so this is all information that you can find online in real time, and gives you some sense of what's going on throughout the lakes in places where there aren't direct observations. So I wanted to just give that high level overview of GLERL and our operational forecast systems. And now I'm going to dive into a little bit of coastal coupling work. And this is some of the ongoing research we have going on in the lab and some of the directions that our future model development is taking. So coastal coupling, when I refer to that, I mean the linking of our lake or ocean domain. In our case, it's the Great Lakes, although they use very similar models in the oceans. So we a lot of times refer to this as the ocean domain in our system, but it refers to linking that wet domain, the lake or ocean, with the overland and riverine domain. There can be a lot of gaps between those two domains in the models, and it's this sort of transitional zone that's not always wet, so it doesn't really belong in the lake. But it's not really a river either, so it kind of falls through the cracks of these models sometimes. And it's important to get those to link up and improve the water budget and improve some of the representation of coastal processes in that transitional zone. So in addition to that floodplain area, a lot of ports and harbors and estuaries are also included in our current Great Lakes models. And so the work that we're doing is to expand the model into some of those critical areas that are important for navigation and infrastructure, and improve our modeling in terms of that navigational guidance, as well as flood and inundation forecasts. So right now we can produce a water level along the coast, but if we expand our models into the floodplain, we'll be able to model that wetting and drying as the floodplain becomes inundated or dries back out. And those are some of the processes that aren't represented in our current model that we're doing work to incorporate. So the first project along these lines that I want to talk about is the Lake Champlain flood forecasting system. So Lake Champlain is, it's not quite a Great Lake. It's located to the east of the Great Lakes over here between New York and Vermont, and extending northward into Canada. It's long and skinny, as you can see in the figure here, more than 100 miles long from north to south, but only up to about 14 miles wide at its widest point from east to west. It has a maximum depth of 120 meters, but an average depth of just 20 meters. So it is still fairly deep, but not quite as deep as the Great Lakes tend to be. Its outflow, it drains north from the Richelieu River, across Quebec, and ultimately into the St. Lawrence Seaway and out to the Atlantic. It's binational, so it's mostly in the US, but a little bit of it is in Canada. And the US portions are very steep and mountainous. It's between the Green Mountains of Vermont and the Adirondacks of New York. And then when you get farther up toward the Canadian side, it's much flatter. There's a lot of farmland and marshland up there. And in addition, the watershed is quite large compared to the size of the lake itself. That's the green dashed line on the figure here. The watershed's about 20 times larger than the lake area, and that can make it very flashy and prone to flooding. And that was the motivation for the development of this system. There was record flooding in 2011, where there was rapid snowmelt from the mountains and heavy spring rain, which led to record flooding. Water levels were above flood stage for more than 2 months from April through June. There were huge increases in the lake surface area and the lake volume, and damage along the shore was made worse by storm surges and waves, which are not currently predicted by the National Weather Service's forecast system there. They use a one-dimensional HEC-RAS model and model the lake basically as a river. So it's a very simplistic model that's currently used for forecasting there. All said and done, there was about 4,000 homes damaged in the US and Canada, over $100 million in damages. And despite most of the lake being in the US, most of the damage was in Canada because, again, that's the part of the lake that tends to be flatter and more prone to that flooding. So in response to that flood and other recent flooding over the last decade or so, the International Joint Commission, who manages water issues between the United States and Canada, um, led and funded this project to develop a flood forecasting system for Lake Champlain. And much like the Great Lakes operational forecast systems that I just briefly introduced, the goal here was to produce uh, up-to-date simulations as well as 5-day forecasts of spatially variable water levels, circulation, and so currents and waves in Lake Champlain and the Upper Richelieu River. Um, this is a high-level schematic of some of the different models involved here. So we're using atmospheric models. We have river inflows from the National Water Model. We incorporate some gauge information. And then the two models we're running are a hydrodynamic model for that water level and current information and a wave model. And I'll talk about some of these in a little bit more detail, but I wanted to show this because it gets to this one-way coupling setup. And so water levels are important in our wave forecast. So we run our hydrodynamic model first to produce water levels throughout the lake and also tell us which areas are currently wet and dry based on the flood stage. And we use water level output from that model as input into our wave model. And that's going to improve representation of waves right along the coast. Those water levels can have an important impact there. And in addition, if we are in a flood scenario, it'll allow the wave model to form waves in flooded areas because the FVCOM hydrodynamic model will be telling the wave model that, hey, there's water in this location right now. And that'll help forecast and simulate the full range of flood impacts along the coast. So like I said at the beginning, I want to kind of walk through the steps of developing a model like this, talk about what hydrodynamic model is, what goes into it, and what we get out of it. And so um, hydrodynamic models are numerical computational frameworks for solving equations of fluid motion. And the basic steps are we discretize the system. So we break it up into some sort of grid. As an example, here's a Lake Superior grid in the upper left here. We impose some forcing. So we have to tell it what the conditions are. If we didn't do that, the water level would just sit flat. We need to say, this is the wind, this is where rivers are coming in, all those sorts of things. And then once we do that, we model the flow between cells. And we're relying on fundamental equations of fluid motion. So the Navier-Stokes equations, like you would come across in a fluid dynamics course, are at the core of a model like this. And so first we start with an existing model framework. In our case, we're using FVCOM for hydrodynamics and WaveWatch 3 for waves. So FVCOM stands for the Finite Volume Community Ocean Model, which was developed at the University of Massachusetts Dartmouth and Wood Hole. And it's a 3D hydrodynamic model. So there's a vertical component to this as well. And that's responsible for those water levels and water currents and so on. And then WaveWatch 3 is also a community model. A community model means it's an open source model that's developed by multiple entities, all contributing to the code and contributing to improvements. And that's the type of model we tend to work with. These are available for free to anybody who wants to use them or contribute to them. WaveWatch 3 is a spectral wave model, so it's simulating wave heights, wave directions, wave periods, those sorts of things. And so we're not starting from scratch. These are frameworks that are well tested and that are well applied throughout the Great Lakes and throughout the oceans and by academics and government institutions alike. And so we start there. Then we develop our model grid. This is the grid for Lake Champlain. You can see the coverage over here and zoom in to get a sense of the detail. So we're using an unstructured grid, which means we're using these triangles of variable size, as opposed to a structured grid, which uses square grid cells, kind of like pixels or a sheet of graph paper. This gives us this unstructured grid where we have these variable size triangles, gives us a little more flexibility, as you can see, to one, follow the coastline well, but also really focus our computational resources on the areas we're interested in. Some of these coastal areas that have river inputs or that are generally going to have more dynamic processes. The resolution of our grid here ranges from about 50 meters in some of these dynamic coastal areas up to about 400 meters offshore. And there's a total of just over 61,000 of these triangular grid elements comprising this grid. We also have 20 vertical layers. So there's a 3D component. And this covers Lake Champlain, the upper Richelieu River here, and then the surrounding floodplain. So in this case, it's not just the lake itself. We do expand up into the floodplain. And so we're simulating that dynamic wetting and drying. And we're using the same grid for both FVCOM, the hydrodynamic model, and the WaveWatch 3 wave model, which allows us to pass that information, that water level information from FVCOM to the wave model and inform those water levels near the coast as well as the wetting and drying in the floodplain. So we have a grid. The next step is to impose forcing. And this is an overview of all the different forcing that goes into a model like this. And so we have river inflows. Those come from the National Water Model. And that's what this image is showing on the right here. These faint blue lines are the National Water Model stream network for the watershed. You can get a sense of how detailed that National Water Model is. And then these darker blue ones are the ones that we're actually using as inputs into our hydrodynamic models. Those are the ones that cross the shore here and represent inflows. We have one outflow, which we're applying as an elevation open boundary condition based on a water level gauge there. For meteorology, we're using the high resolution rapid refresh, which is a state of the art weather model. This is probably what you're seeing in the forecast, again, on your evening news. This is the same sort of forecast models that weather forecast offices rely on. And so we use that to inform the wind conditions and the overlake precipitation in our model. We also, we run this 4 times per day, and after each of those runs, we compare our results to a series of water level gauges along the lake and apply a little bit of extra precipitation or evaporation to make up for any error in our model. And that keeps it from drifting over time. So it's sort of a crude data assimilation method. And then again, the wave model has water level forcing from the FVCOM hydrodynamic model. We run the FVCOM hydrodynamic model first. Once that finishes, we processes the output as input into the wave model to better represent the water levels. And then the wave model has some crude ice forcing as well. There's not a good source of ice data for Lake Champlain like there is for the Great Lakes. So we worked with the National Weather Service in Burlington, and they kind of sketch out the boundary of ice based on clear sky satellite imagery. And we use that as an ice mask in our model. And that we know that we're not going to get big waves in heavily ice covered areas. And so that just is a way to represent that ice cover in the model and damp those waves there. And so once that's all set up, we have our grid, we have the conditions. That's really all we need. And so at that point, we can run the model. We run these on high performance computers or HPCs. You might hear that referred to as a Linux cluster or as supercomputers, different words for the same things. And those are essentially a system of processors that are networked tightly together so that they can distribute the computational workload of these complex problems across more than just a single computer. So here at GLERO, we have local HPCs that we use for experimental purposes. We develop models and run them here. And then once again, they go through that testing and validation phase. We'll transition them to an operational center, and they have operational HPCs for running those operational models. And a lot of these weather forecasts and lake forecast models all run on the same supercomputer so that since a lot of them are tightly linked and use output from one to inform another, all of that ends up on the same high performance computer, and you can one model can readily access data from another. So we often run these on 10 to 1,000 computer cores. For scale, your laptop, a typical laptop has about 4 cores. And so the Lake Champlain model here runs on 224 cores at GLERO and takes about 45 minutes to complete a 5-day forecast. And so that kind of gives you a sense of the amount of computational resources that go into to running these sorts of models. And even with a high performance computer like this, it's still not something that you press a button and get a result right away. A lot of times we're trading off resolution for performance. there's nothing that would stop us from generating really high resolution models, but it would get to the point that we couldn't run them at real time. And so we're trying to balance, high quality, high resolution results with what's feasible from an operational real time standpoint. So these are some water level outputs from our Lake Champlain model. These are time series from some simulations we did for 2017, which was a minor flood event um, at 4 locations throughout the lake. And I'm showing observations in black, results from our model in red, and then results from a model without wind in blue. And water level on the y-axis and time for about a month-long period is on the x-axis. And this is intended to show that the improvements that a 3D model like ours will have over the existing one-dimensional forecast system. The existing forecast system, again, is one-dimensional, so it's not going to include those wind-driven storm surge effects. And it also doesn't include waves, but I'm not there quite yet. But you can see these short-term fluctuations in water level that are currently occurring frequently throughout the month-long period here. And those are storm surges when you get a strong wind blowing along the long north-south axis of the lake and pushing water to one side of the lake. So you get a rise at one end of the lake and a corresponding drop at the other end of the lake. And so you can see we're capturing these really well in the model compared to observations. And you miss them completely if you don't include those wind effects. And so this will give forecasters information on not just when the lake may flood, but where those impacts may be most severe, which is important for forecasters. As part of the wave modeling, we deployed a wave buoy on Lake Champlain in 2021 and 2022. For a lake the size of Lake Champlain, there was very little data on wave conditions. And we don't want to just make models and assume they're right. We really want a data point that we can compare to and assess the skill of those models. So we deployed this in collaboration with the University of Vermont, who has a research boat there, and collected these 2 seasons worth of data. And they were available in real time on the NDBC website. You can still get the data there. In fact, that's the same place that you would find data from a lot of the Great Lakes buoys, including the buoys operated by Jay's lab here at University of Minnesota Duluth. So these are a comparison of wave height results to observations observed in black and modeled in red for the 2021 deployment season. It's pretty noisy, so it's hard to make out the trends too well, but we're capturing the moderate wave events pretty well in here. The model has a tendency to underestimate them more than it overestimates them, but for the most part, it's getting the timing and magnitude well. The correlation plot matches pretty well as well. We were a little disappointed because COVID restriction, or really logistics due to COVID, limited the amount of time that we could get the boat. And so we had to pull them pretty early in early October here. And it was late September this year. And you tend to see the biggest waves as you do in the Great Lakes in the fall months or early winter months. And we would have liked to have the buoy out there. You can see the biggest events we got here were about 2.5 to 3 feet. We've heard that waves on Lake Champlain can get more like 8 to 10 feet, and it would have been great to capture some of those events and see how the model does during those big wave events. But we worked with what we had, and the model seems to be doing pretty well based on the 2 seasons of observations that we were able to get. So pleased with the performance of the model there. And then again, these run in real time. So we run our nowcast 4 times per day to catch the model up to the present conditions. And then once per day, we generate a 5-day forecast using those nowcast results as our baseline conditions. And we produce hourly outputs of all parameters of interest. The hydrodynamic model we've had running since 2019 and the wave model since August 2020. And these are available. Again, you can go to our website and see these results from our model where it's running experimentally until we transition it to operations. And you can get time series graphs similar to what I just showed you, as well as forecast animations for all of these different things. And so I'm not sure how many of you would be interested in Lake Champlain specifically, but you can imagine how if you live around the lake or have a cabin on the lake or a boat on the lake, this would be a very valuable resource. And so this is intended to both improve forecasting. We would our primary customer here is going to be the National Weather Service, who will use this sort of information to guide their forecasts and issue advisories. But if you do have a boat there and you want to go boating the weekend, you could actually get a 5-day forecast of waves and get a sense of, whether it's going to be safe to go out or not. If you have a cabin on the lake, you can see a forecast for water levels at your specific location. And those are the types of uses that, we would get from a model like this. And so I kind of wanted to present that as kind of a holistic view from beginning to end of development of these models. But I want to close with some work that we've been doing in the Great Lakes and specifically in the Duluth Superior Harbor. That's very similar to the coastal coupling work that we're doing in Lake Champlain there. So I'm preaching to the choir on this, but the Great Lakes support an extensive shipping network with economic benefit to the region and really to the world. There's some international shipping here as well. And so coastal infrastructure supports that commercial navigation, as well as things like flood preparedness and resiliency. And, there's a lot of recreation that goes on in the harbor as well. But like I mentioned at the beginning, a lot of these ports and harbors are not represented in our current Great Lakes forecasting systems. And a great example of that is the Duluth Superior Harbor. And so this is a figure showing the grid of our current hydrodynamic model for the Great Lakes Operational Forecast System. And you see those triangles again for this triangular unstructured grid. And you can see it ends right at the boundary of the lake itself. It doesn't extend up into the harbor or up into the estuary. And then all these blue line segments are stream segments in the National Water Model. And you can see they also end right at this harbor estuary boundary. And so essentially the river model is treating this area as a lake, and the lake model is treating this area as a river, and it's falling through the cracks of these two modeling systems. So as part of this National Ocean Service Water Initiative project, we had the goal of linking these hydrologic and hydrodynamic systems to link these domains and improve coastal forecasting in this area. And this is a test case for more work that we want to do along these lines throughout the Great Lakes. I won't go through all these details, but it is a similar model setup to some of the others I've talked about. So we're using FVCOM for hydrodynamics. It's an unstructured grid that gets to very fine resolution. In this case, we have resolution as fine as 10 to 15 meters up in some of the estuary areas. And then since we're really focused on the estuary in this case, we want to include Lake Superior. So we capture those lake impacts on the estuary, but we're not trying to model, do a great job modeling the lake itself or get into a lot of detail up there. So we coarsen the lake a lot and reduce the resolution to 10 kilometers in the offshore region. And this is actually based on a grid that we developed when I was working in Jay's lab for the estuary. And we've just kind of used that as a baseline, dialed up the resolution in the estuary and included some of those floodplain areas so that we do link up with those rivers. And this grid here has about 340,000 triangular elements. And we ran simulations for October 2019, which was a lake storm surge event, and June 2012, which is a heavy rainfall flood event. Similar meteorological forcing, we're using the high resolution rapid refresh for 2019. That model didn't go back to 2012, so we're just interpolating available observations for the 2012 case, which isn't quite as fine resolution as the HERB, but it's the best we have. And then for river forcing, we're using the USGS gauges for the two major rivers, the St. Louis and the Nemadji, as well as the St. Mary's River outflow over in Sault Ste. Marie. And then we have the 24 smaller tributaries from the National Water Model that enter the estuary there. And again, this is dynamic wetting and drying, so we're capturing inundation and drying of the floodplain portion of the grid. One of the main dynamics of the lake affecting the estuary is the Lake Superior seiche. The seiche, if you're not familiar, is the sloshing of water back and forth across Lake Superior. You can think of it kind of like a giant bathtub in response to a wind or pressure setup that initiates it. And that's what I'm showing here. So these are water levels on the left, and you can kind of see the water levels rising and falling at the eastern and western ends of the lake at regular intervals and corresponding rises and falls in the estuary water level here. You see currents reversing in and out of the Duluth entry, where I have zoomed in here. And then just as a tracer, I'm plotting surface temperature, and you can kind of see that exchange of water between the lake and the harbor. And so the first comparison we did is measurements of flow. So I should go back. I didn't point these out, but there's a flow gauge at the Duluth entry here and a water level gauge just inside the harbor, right next to the Blue Heron, in fact, if you do any work on that. And so these are some of our main comparison points. And so the first comparison I'm doing is looking at flow at the gauge in the Duluth entry here. And so observations are in black, and then derived flow from the model is in red. And you can see again these regular fluctuations at this characteristic 8-hour interval for the Lake Superior Seiche that we're capturing the magnitude and period of quite well. In this case, we're actually capturing the phase pretty well too, although we've found that the phase has a tendency to drift. So we're really interested in whether we can capture the period of this and the magnitude. And we're doing a really good job of that with this model. You can do spectral analysis to look at it that way. And so this is looking at the magnitude of the signal at different periods. And at the 8-hour period, you can see that's the dominant period in both the model and the observations. And again, we're matching that curve pretty well. And so that's great. We're capturing that exchange between the lake and the harbor quite well, which is going to be a key feature here. We can extract that Seiche signal, do the same sort of spectral analysis at every node in the model, and extract the mode of that Seiche signal. It's going to be weakest in the middle of the lake and strongest at the two ends. But if we zoom in on the estuary, we can see that it increases in strength in the model up to about this location here, which is the Oliver Bridge. That's a place where the river gets pretty narrow. And in our model, at least, that sort of represents the extent of that lake influence, which is more than 10 miles upstream. So the Lake Superior is having a big influence on the harbor and estuary pretty far upstream, which is, I think, no surprise to people that live in Duluth. I think we're all aware that the lake has that sort of impact on the estuary. There are some water level observations from the Lake Superior NER over in Superior that also confirm this increase in strength up at least to the Oliver Bridge, and then there aren't any observations beyond that to confirm the kind of reduction in strength beyond that point. But this is kind of interesting because it allows us to characterize the extent of Lake Superior's influence, at least by one metric. So the two events that we're looking at here are the October 2019 storm surge and the June 2012 flood. So start with the October 2019 event here. This was a storm surge driven by high winds down the western arm of Lake Superior and a strong pressure gradient along the lake. There were winds over 70 miles per hour and waves over 10 feet tall. And damage along the shoreline was made worse by high lake levels at the time. So there was a lot of damage to shoreline infrastructure, which again, for people, those of you who are living in Duluth at the time, you're well aware of all this. So these are time series of water level from Duluth Harbor for that event. This is for the entire month of October 2019. And really just what I want to show you is that we captured this peak in water level quite well. The observations are in black and the model is in red. And again, you see these high frequency 8-hour Seiche fluctuations, which the model is doing a good job of capturing well. So this is really the only piece of data other than the flow observations I just showed you to go off of for this event, but we are capturing this maximum water level very well with the model. Want to go now to the 2012 event. We have a little bit more data for this one. This was a heavy rainfall event where there were 2-day rainfall totals of over 10 inches and a lot of damage, washouts to roads and bridges. Over $100 million in damage in total. And I was in Duluth at the time for this one. It was a pretty catastrophic event. This was the first summer during my master's there. This is a similar time series of water level for 2012. Again, we see these regular Seiche fluctuations. We don't quite capture these biggest peaks here right at the time of the flood, although we do capture the persistent rise in water level from right before to right after the flood. So, overall, it's doing pretty well. Not entirely sure why it's missing these peaks. It might be that some stormwater inputs are not represented in the model. It might be that we're using a little bit less sophisticated meteorological forcing than we have in 2019. There might have been some anthropogenic inputs as well. There's some news articles talking about how they opened the dam upstream, which we wouldn't capture in the model. So we missed some of these real acute peaks in water level, but we did capture the overall rise. So pretty well overall at capturing at least the persistent impacts of this event. What's interesting here, though, is we actually have some surveys of flood extent for the Duluth River. This is for the Fond du Lac neighborhood, which is located at the upstream portion of the estuary here. These were surveyed by USGS and Army Corps of Engineers and the city of Duluth, and then interpolated to produce these maps of flood extent. And this is a very rare type of observation to come by. So when we're doing this sort of modeling work and we want to model this dynamic inundation, we don't have a lot to go off, but this is one source where we do. And so this is an animation showing the dynamic wetting of our model during this event for that neighborhood. And you can see the water expand from the nominal river boundary out to particularly the northern portion of the floodplain here. There's houses all along this peninsula. This is Highway 23 here, I think, and then this is the Fond du Lac neighborhood up here. So a big chunk of that gets flooded in the model, and as you saw in the inundation map. And so if we compare the maximum inundation from our model in red to the observations in green, you can see that it's matching up very well. If we put a number on it, observed maximum inundation extent was 906 acres and models was 911 acres. So very good by that metric, but just visually looking at it, you can see it matches up quite well. And so again, this is very rare. It's hard to model or hard to validate models for this dynamic inundation. And in the case where we do this, this gives us a strong indication that models can be reasonably used for this sort of spatial inundation application. This is just a similar plot showing maximum inundation depth, and just visually looking at it, this is more of just a qualitative comparison. You can see it compares quite well between the observations on the left and the model on the right. Similar conclusions to what I showed you on the last slide, though, in terms of flood extent. And lastly, we can look at the influence of these tributaries on currents throughout the estuary during an event like this. The scale isn't too dynamic in this case. I could have maybe zoomed in on the entrances here where it's most impactful, but this is plotting the difference in currents between when we only include the major rivers, so the St. Louis and the Nemadji, versus when we include all of these smaller tributaries that aren't currently included in our forecast models. And what we find is that during that June 2012 event, including those smaller tributaries, increased surface currents in the entrances here by about 40 centimeters a second, which is very substantial in a system like this. And that's important because there have been some ships that have gone off course in the harbor. Here's a news story about one of them, and we've spoken with the National Weather Service there, and they said that currents probably played an impact in it. These are, ports and harbors like this can have fast changing currents. There's a lot of navigation, and it's not being forecast currently. And so expanding these models into ports and harbors like this and capturing and ideally forecasting some of those changes in currents as we incorporate more of those rivers and improve the water balance might allow us to provide better navigational guidance and avoid some of these incidents. And I think it goes without saying that the type of forecast that flood guidance would be used for, it would allow people to have a little bit more advanced warning and take some measures to protect their homes and protect their properties from that sort of flooding. And so these are a couple of the types of applications that these sorts of expanded models could have. And so in the future, we want to expand our models into other Great Lakes ports, harbors, and floodplains. The Duluth Harbor here was just an example because it is a major shipping port and had a couple major flood events we could look at. we want to optimize our models for real-time operations. And so the model I just show you is very high resolution. This gets back to the balancing accuracy with performance. It wouldn't be feasible to run in real time. In fact, it doesn't run much faster than real time. A 24-hour simulation in that model took about 16 hours to run on our 224 cores. So it's okay for research, but if we wanted to run this in real time, we would need to reduce the resolution a bit and find a good balance. We have a 5-year project to develop a next generation forecast system for Lake Ontario specifically, which is going to be focused on improving forecast guidance for flooding and inundation, expanding into some of these ports and harbors, and improving navigational guidance as well. We're focusing on Lake Ontario because it's had a lot of flooding issues in recent years, but we anticipate that methods and frameworks we develop from Lake Ontario will be readily expanded to other Great Lakes and really serve as the next generation Great Lakes operational forecast system. And so in the future, our vision would be to have the Great Lakes operational forecast system include all of those floodplains throughout the Great Lakes and all of those ports and harbors, and be able to produce that sort of those sorts of forecasts on spatial inundation extent, like I just showed you for Duluth. So I'd like to acknowledge a number of collaborators on these projects, in particular, other people at GLERL, the Cooperative Institute for Great Lakes Research at University of Michigan, International Joint Commission, who funded the Lake Champlain work, and NCAR, who helped expand the National Water Model, and then National Ocean Service, we've been collaborating closely with on the Duluth Harbor project. And with that, I'll thank you for listening, and I'm happy to take any questions if there's time.
Dan, I'm wondering, could you speak a bit about the transition from the Prince Ocean model to the FVCOM?
Sure. So the Princeton Ocean Model, or POM, is that's the first generation Great Lakes operational forecast system. That was a regular grid model. So it used a series of interlocking squares, all same size squares. Again, you can think of it like pixels. And so the grid looked very pixelated. It ranged in size from about 5 kilometers to 10 kilometers. And so the recent upgrade, the transition of the FVCOM model, represents version 2 of the Great Lakes operational forecast system. So the transition has been kind of ongoing. We run these models experimentally for a long time so that they're well tested and validated before we transition them. And so the Princeton Ocean Model went back to sometime around 2010, 2012. It was before my time at GLERL. But yeah, recently with the upgrade of these, the Princeton Ocean Model is not used at all, and all the models are FVCOM based now. They use this higher resolution, unstructured grid. And so I don't know if there's any more specifics than that you're interested in, but it does create some issues when you're trying to do longer term comparisons, because you're going to get very different results from a coarse regular grid like model like that than you are from FVCOM. And so the FVCOM model, again, Lake Erie goes back to 2016, but Lake Superior, for instance, operationally only goes back to 2022, last month. But you can go to GLERL's website. We'll have archives of the FVCOM model going back to probably 2016. So there will be a little bit more overlap than there is available on the operational archives. I'm happy if there's any more specific questions than that. We can go into specifics more. But yeah, the short story is that that's the older version. It ran from 2010 or 12 to recently, and now we've transitioned to the FVCOM models. And anytime, I'll also add that anytime we do an upgrade like that, it can't just look pretty. One of the criteria is that it has to provide the same or better results than the model before it. And so that's when we're validating and testing these, that's one of the comparisons we do. Is it better than the model before it, which in this case was the Princeton Ocean Model based GLOFs that came before it.
I kind of have two questions. So the first one, how do you generate the unstructured grid? Is there some computer algorithms or is there some sort of human inputs?
Yeah, it's a good question. The way we've done it, we use a software called SMS, Aquaveo SMS. Um, and I've heard it described as kind of a bridge between science and art. It's all based on data. So a lot of times you're starting with shape files of the shoreline, DEM, digital elevation maps of the bathymetry or topography when you're getting to the floodplain. But then you're doing some manual decisions as well. I want this portion to be this resolution. I want to adjust this. But more and more, people are developing algorithms that can do a lot of that work for you and um, kind of automate the process of increasing the resolution in areas where the bathymetry changes more rapidly, and that sort of thing. I don't think there's a perfect algorithm yet for doing it, but there is um, more and more different software packages and algorithms that are able to do a lot of that work for you and get some of the manual parts out of it. But yeah, it's a very
That's
good question. That's one of the most labor intensive and one of the most important parts of a model like this is developing the grid. That's a real big portion of the work that goes into creating a model is the grid.
and is there a way to estimate how confident are you in using the model as a prediction?
Yeah, so we'll use sort of standard statistical methods like bias or root mean square error for the different metrics. Um, you can compare it to in the case of something like water level, you can say, how much better is it than just predicting no change in water level? You could use that as the null hypothesis. But yeah, there's a lot of those, bias and root mean square area are probably the two that we look at the most for those sorts of time series type estimates. And there are standards from the National Ocean Service, who is the operational center for these models. It has to meet these criteria in order to pass their tests to go into operations. And so those are some of the things we look at.
Right, like compared to the past observations.
Yeah, you would compare it to the
Okay,
past observation. So it's always going to be you're always going to be looking at the past to validate the skill.
right.
But you can do what we call reforecasting as well. So you can say, this is the forecast we would have gotten last year, and you can compare it at different forecast horizons. So this is the bias in real time. This is the bias for our 1 day prediction, our 2 day prediction, so out. And you do see a decline in skill as you get farther out into your forecast, typically. Yeah,
Thank you.
good question.
Questions here? How much potential does Lake Superior, how much potential does Lake Superior itself, without storm surge, have to flood any town around Lake Superior, say Ashland or Bayview, or pretty low? Can you hear, Dan?
I can hear. I think it was difficult, but I'll repeat the question and see if I got it right. I think the question was, if we ignored the impacts of storm surge, is there any area of Lake Superior that would be likely to flood based on kind of just water levels alone? Is that the gist of it? If it is, I think, honestly, I don't have a good answer for that. There are my realm is this sort of short-term 5-day hydrodynamic modeling. There are other groups at NOAA who would be a better resource for that sort of thing. In particular, there's an office called the Office of Coastal Management, who I think would have some great products for that. They actually have some tools you can look at where you can sort of take a slider and just raise and lower the water level, and it'll show you the areas that would be flooded under that water level scenario. And so that, I think, would probably be my suggestion for how to look at that question. But I don't have a great answer
I think
offhand.
part of that is that the St. Mary's River is a strong positive feedback on something like that. In other words, the higher the lake level, the faster water is going to be flowing out the same areas. And so it's really difficult, it turns out, to get lake levels much higher than they already are. And it's these wind-driven events where suddenly there's a meter of water, extra into the Blue Harbor. That's where you're never going to get another meter of water on a steady basis in Lake Superior, other than in a completely different precipitation regime. So, Dan, I have one quick question. I think we're going to go after that. Unless, I'm sorry, do students have questions? That's the priority here. Go ahead, Rhian. Well, no, but Dan, did you get that?
No, I didn't. Sorry.
So how do buoys measure wave height? I can take this, but this is your end of your general exam.
Yeah. It's generally done, at least as far as I'm aware, with an accelerometer. So it's measuring the acceleration of the buoy up and down and capturing the spectrum of those waves, and that's the gist of it.
Yep. Does that answer your question? So basically, you have a sensor that can measure the acceleration. Your phone has an accelerometer that tells it about how it's moving around and stuff like that. If you imagine that sensor sitting inside of a buoy, wobbling up and down, you can take that motion and use a set of complicated transfer functions that says if you're getting this kind of you're getting X acceleration, that means the waves are Y meters tall. And what's more, because it's doing this instead of this, the waves are going in this direction, blah, blah, blah. So, yeah. So my quick question, Dan, is what's the status of sediment modeling with these GLOFS models?
Of what modeling, sorry?
Sediment modeling?
Oh, sediment modeling. Yeah, not much. I haven't done anything with that, and I'm not aware of anybody at the lab that's done anything with that. I think it's an area of interest. The one, probably the closest thing to sediment modeling we have right now is the harmful algal bloom forecast, which is a model that takes the GLOFS output for Lake Erie and takes a recent satellite image to as initial conditions for where that harmful algal bloom is, and then it uses particles, including buoyancy, to track their movement. So it's not capturing the decay or any of those biological processes, but it's modeling them as buoyant particles. That's, I think, the closest thing we have to sediment modeling right now, but there is interest in pursuing that more. So I would say it's in its infancy at best.
Gotcha. Thanks, Dan. So again, thanks so much for taking the time to speak with us. We really appreciate it. You've got quite a big audience here online and in the room. And I have a bunch of questions that I'm not going to bother you with right now, but I'll follow up in an email. So
yeah, sounds great. And likewise, I had my email at the end, and Jay has it. So if anybody else wants to follow up by email, feel free to reach out.
Okay. Thanks again, Dan. Have a good
Yeah,
evening.
thanks for having me. I appreciate it. It's good to see everybody.
Good night, everybody online. Bye.